Yeah, thank you very much for coming. It's late, and you might have heard many talks already. And I'm grateful that you are still interested. So let's start. I want to talk about microservices, Hystrix and RxJava, and especially about which role they can play in modernizing existing systems, because normally we are not in the position that we can build a system from scratch. We have to deal with software that is ugly, that we don't like, and that we want to get rid of. And so I always ask myself, when I see new technologies, how can they help me to improve my real current working situation? I don't want to be too abstract, therefore we talk about this fancy startup that started a long time ago in the 90s with some e-commerce site, and they became very successful pretty quickly, and they never had time to modernize their system properly. So they ended up with a pretty monolithic systems architecture, and that looks similar like this. There is some big application in the middle with some external dependencies. We also have a marketplace in our application so that external merchants can sell their products on our platform. We have dependencies to external payment providers that process our payments. We have a database. We have pretty much we are pretty much dependent on other systems. And that causes some problems. It's really hard to maintain the application right now. Every new feature takes a lot of time to develop because we have side effects. We don't know where to change code because it causes errors in parts of the system that we don't expect. It's very unstable. Our developers have to get up in the night because the platform is crashing. We are still on Java 1.5, and we would really like to update, but it's not possible because we don't know how our side effects will cause problems, and it simply doesn't scale. We can't have multiple servers because everything is just this big system that can't be scaled in a proper way. It would be really nice because it's such a hype to introduce microservices, but I don't think that this is a good idea in this situation because the system is still very unstable and we haven't learned how to deal with external dependencies. And therefore, it's a good idea to think about the stabilization of our system first. Because that would gain the ability for us to act again on our system. And when we have gained that, we would be able to improve our system later. But the first thing is really we want to have a stably running system that doesn't cause so many problems. So why does it cause so many problems? It's because we have these external dependencies, and we didn't think enough about what this means for our application. That means we have the situation when one of these merchants, for example, is not available, our complete platform crashes. Why does that happen? We have just this main application thread pool in our application, and every time we send a request to the merchant and we don't get an answer, it blocks our main thread pool, and that causes in the end cascading failures. That means just because merchant system 1 is not available, the complete thread pool blocks and our application is not able to receive any requests anymore. Yeah, so the customer doesn't see anything, and yeah, the complete platform is simply down. And that just because there is just this small merchant system that is not available. That is a really bad situation. And the question is, what can we do about it? There is this really nice book from Michael Nygaard, Release It, that describes how real production-ready software should look like. And he describes several stability patterns. And I want to have a look in more detail in 3 of these patterns. The first one is a timeout. The timeout is well known. Many clients offer the possibility to configure something like that. And what does it mean in the end? It simply means that at some point it simply doesn't make sense to wait for a response from a client that doesn't answer. Yeah? At some point it makes really sense to consider a request to be failed and simply stop waiting and simply return an exception to the calling to the client. And that already prevents us from blocking the complete thread pool just because everybody is waiting. Yeah, after this, Another pattern is the bulkhead pattern. Bulkheads are these vertical vaults inside of a ship, inside of a body of a ship, that create watertight compartments. So when the body of the ship or the ship runs into an iceberg, we are protected against sinking because the water can just spread in one of these compartments and not over the complete body of the ship. If the leak is too big, it still can happen because that's a picture of the petite Titanic, but it's still a good idea. And also, you can transfer this pattern into IT. So thread pools build something like that, database connection pools, instances, server, data center. They build areas that are completely independent of each other. So if one of these areas is failing, there are still others that can still work, and so they protect of a complete fallout. Another pattern is a circuit breaker pattern. A circuit breaker pattern, the circuit breaker we know from our electric circuit in our household. Yeah, so if the voltage in our circuit gets too high, it opens and interrupts the circuit, so to prevent further damage. And we can also use a similar pattern in our software. That means we have a external system that we want to call, and in the normal state, the circuit breaker is closed, and every request goes through to the external system. But at some point, we detect that we don't get proper answers anymore, and we just have failed responses or no responses, and at this point, a circuit breaker decides that it doesn't make sense to call the external application anymore. In this case, the circuit breaker opens, and the other application is not called anymore. We do that because the other application has to recover, and that's not possible if the load is still high, and it's simply not working. And to find out if the other application is running again, there is still this, there's also this half open state. That means in a certain period of time, the circuit breaker simply tests if the other application is available again. And I don't know, it sends one request each minute, and if this is successful, it goes into the closed state again, and the external application is called again completely regularly. So that sounds maybe a little bit complicated to implement it yourself. And the nice thing is that there is a library called Hystrix from Netflix. And this is implementing already all of these mentioned patterns. It's from Netflix, and yeah, it implements a command pattern, or you can use it with a command pattern. And the very nice thing about Hystrix is that it comes with metrics and a dashboard that I will show a little bit later. And what I want to do now is demonstrating how to integrate Hystrix into your application. We take a pretty simple use case for that. We simply want to search for products. And to do that, we have to, a client is simply requesting products in a certain category or so. And our application has to call all of these three merchant systems in this image, and also the database for our internal products. And normally we expect an answer like that. Yeah? So we have products from our internal systems, we have product of all merchant systems, and we return them in one response. In a normal situation without Hystrix, yeah, this is an example where we simply use a Jersey client, and the create is underlined because we don't give any configuration parameter there, and that means that the client isn't using any timeout. That means that as soon as the merchant one system has any problems, we get exactly these cascading failures that I talked about before. And yeah, our application will crash finally. So, and now we try to integrate Hystrix into this. The nice thing about Hystrix is that it's simple, really simple to integrate it into your application. So the only thing you have to do is to wrap your call, this is this call, into the run method of the so-called Hystrix command. And in the next step, you simply execute it. So you create a command with some parameter, in this case a query, and you call execute on it, and then you already have exactly the functionality that I just described before. Yeah, so you have a timeout, you can configure a thread pool that is based on command groups. Yeah, so you can think which external dependencies should have their own thread pool, and simply configure these Hystrix commands. It's pretty easy. And you also have this circuit breaker in place. The nice thing about that is also that you can simply decide with the same command that you don't want to execute it synchronously. You can also execute it asynchronously. That can be achieved by calling Q on the command instead of execute. In this case, you get a future back, and you can collect the results later. So in this example, these two calls to the merchant systems are already happening in parallel. Yeah. The question is, what happens when the circuit breaker opens? Yeah. In this case, we don't get any result. Normally, when we don't do something more, we receive an exception from Hystrix. But we also have the possibility to define a callback. The callback or the get callback callback was wrong. Fallback. In this case, Hystrix calls the get fallback method of a command, and yeah, we have to think what is a reasonable fallback in each scenario. In our case, it's pretty simple because when there is no merchant system available, we simply return an empty list. It's not really a problem. It simply means that the customer can't buy anything from this system, and yeah, he still gets a reasonable answer. So in this case, he still gets back 5 products. Just one is missing, but yeah, that's actually not so bad. Yeah, so the customer doesn't see anything of that. The merchant that has an unstable system might be sad, but yeah, he's responsible for the system. And yeah, that's pretty nice. So we already have improved our system stability dramatically by this really small step. And now we have yeah, all external dependencies protected by Hystrix. We have defined thread pools, and yeah, we are finally able to think about further steps. And we are also able to monitor our application in a nice way. Now I want to show you the Hystrix dashboard. This is actually this. So you can integrate an servlet into your application that simply publishes an ongoing stream of events in your application. And Hystrix offers also a dashboard that can read this stream, yeah. And what you see then is something like that. I have 4 merchant systems in my example, and 2 are actually yeah, having a timeout sometimes that happens randomly, and 2 of these systems have an availability of 100%. And you can see that all circuits are closed. And yeah, so we don't have a real problem. Some systems are not completely stable, but it's okay. And now I want to show what happens when one of these systems stops completely. So I'm stopping one of these, and now you should see that one has really big problems. Merchant 4 has a error rate of 100% now, and the circuit opens. So at the moment, no request will be sent to this merchant 4 system anymore. And yeah, but our system, our own system still works perfectly, so stable, and we don't have any problems. Now we see what happens when I start system 4 again. Yeah, everything's back to normal. And the nice thing about that is really that it's really so easy. Yeah, I showed you what I did, and that's exactly what I did. It's nothing more. Yeah, so when you simply try to identify the external dependencies of your systems and you integrate Hystrix into them, even your old legacy application, yeah, can gain a lot of stability. Yeah. So the question is, now we have a stable an almost stable system, but we still have the problem that we can't react to our business in a fast way because everything needs so much time. And yeah, as I said before, the reason for that is that we have this monolithic architecture where everything depends on everything. And it would be really, really nice yeah, to have smaller units in our system that we can understand, that we can replace more easily, and yeah, so that we would even be able to introduce new technologies and that everybody has more fun while working. So what we need is a clear cut, but the big question is how to get started. Yeah, we have this monolith, and that's really not yeah, an easy application to maintain, and we want some smaller boxes. So which decisions do we have to make? We have to make decisions on 3 different levels. The first one is a domain architecture that mainly means yeah, how to cut the systems. The macroarchitecture means, yeah, I don't know, what do all these systems have to agree on? And the microarchitecture is actually the level of where each system can make decisions for themselves. So, and the nice thing about the domain architecture is, and that is even an advantage compared to a greenfield project, when you maintain a monolith for a long time, you already know the domain a lot of better than when you just start a new project. Yeah, so it really makes sense to analyze how the current system looks, which dependencies you have inside of the system, and yeah, to get an idea which cut actually might make sense. Normally when you talk about microservice, you always hear this bounded context thing that is known from domain-driven design. I think that's a pretty good idea. So you really should analyze your business dependencies and have a look on what really belongs together, and that should be in a single system. And then we have the level of the macro architecture. This is just an example. On the left side, you have the areas where you have to make a decision. On the right side, we have an example what we would do with this system now, but you can make your own choice. So we would integrate it with APIs that, but also that's something what we do in our company a lot is every of these systems would have its own user interface, and we would integrate that on the user interface layer also. So that means we would do that by linking user interfaces to each other, but every system would be responsible for its own, so that we don't get a monolithic user interface in the end anymore. Yeah, I don't know. For deployment, I wrote Docker because it's also a nice hype. But yeah, as formats, we would use JSON. We would use HTTP as a protocol to communicate on an API level. In general, it's a good idea that you can really mix languages as you like, as long as each system can make its own decision. So you shouldn't have any or too many library dependencies between systems. But of course, on a company level, it also makes sense to reduce choices because, you still need the people who understand these systems. But in general, between systems, there shouldn't be any language dependencies, I think. Then there you have the microarchitecture. This is also an example. Yeah, we are talking about a search example here, and so I don't know, the team that would be responsible for the for the search service could, I don't know, for example, makes the decision we want to use Spring, we know it pretty well, we like Java, so we go for that. And because we are a search service, it makes sense to use a database that is specialized for search. So we have a general idea of where we want to go now, but there is still the question, how do we come from this big monolithic block to this, smaller units? First approach would be Big Bang. So you simply start with building all these new systems in parallel, and you use still the old monoliths in production. The big question is if this really works, because of course you have many bug fixes in the current production application, and you would always have to do the same fixes in the new microservices world, and at some point then of course you would switch. But yeah, I don't know. I'm critical that this really can work. An alternative is a so-called Strangler Pattern, where we have still in the first step our big monolith, but we would simply start working on the current application that is still in production, and it stays in production. So we would try to give it a much better internal structure. Here's also the question if you try to structure the complete monolith in a better way, or if you simply start with a certain area. In our example, we want to focus on the search problem, so maybe it's a good problem, a good idea to simply, in the first step, to give clearer interfaces just for the search domain. And in a second step, if we have then our internal search module in our monolith, we could start to extracting this functionality and to move more and more features into this external search service. And we would have some kind of toggle that could decide if this search request is still handled by the internal module, or already if there is already a functionality in this new search service, and so it could reroute it to this. And at the point where this external search service is complete, we could simply get rid of the internal one, and so we would be already in the nice situation that one functionality of our system is already extracted. The next thing would be to have these other modules extracted, like inventory service or product service. Yeah, looks pretty easy. The question if it's really so easy, the problem of course is that the one thing is to have a nice idea, and the other thing is to you have a real situation, a real running production software with real dependencies, and of course it can be pretty hard. You have to make many decisions if you want to reuse your code, if you write this new shiny microservice from scratch. So you have to make many decisions on your own, and I can't give you really recommendations for that because every situation is different. But it helps to have a clear idea where you want to go. So the next step is, now we have already some boxes extracted. The question is how to connect them in our search use case. What we want to achieve now is, when a search comes in, is that we talk to all the merchant systems. We have a product system that is responsible for the maintenance of our products themselves. So each detail which attributes they have and so forth. The inventory system is actually responsible for how many of these products are in stock and to maintain that. And for a search, we have to call also the product system and the inventory system to get all these details. And and the question is how to do that. If we do that in the traditional way, we would do that in a synchronous way, and the red parts are simply the time that we spend on waiting while we wait for the answer of these external systems. And you see, it's really, I don't know, most of the time we are simply waiting, and the green part is the time when we are actually processing something. And the question if it really makes sense to add this waiting time simply synchronously. So an alternative would be to do these stuff in parallel. So we would simply spend less time in processing our search request. If you do that in a traditional way with futures, you have to do a lot of stuff manually, and you always have to return into a blocking mode because you have to collect the results again, and then you have to use them as an input parameter for the next requests. And it's a lot of work, and if you want to get rid of this blocking parts, you would have to wrap this stuff again into a future, and it's really not nice, and therefore it's worth a thought to introduce RxJava, about what I want to talk about now. RxJava are reactive extensions for the JVM. Originally, these reactive extensions were created by Microsoft, and they are a way to create asynchronous streams, and they combine elements of an iterator pattern, observer pattern, and elements of functional programming. The main difference is they have a very similar interface, but the big difference is that an iterable uses pull and an observable uses push. And the consequence of this is really big because it completely changes the direction of the data flow, and you can do stuff that you couldn't do when you just would use pull. And everything in this model turns into a stream. And what this means I will show in an example in our defined use case. So you have to think about RxJava as something like, you have many parallel streams from different sources, and you have operators to combine them, and and to also change or transform streams themselves. And in the end, everything can flow together, and you have the result that you are expecting. I try to be more concrete. So there are many ways to create observables. These are just a few of them. You can simply put already existing objects into an observable. You can transform existing lists, for example, collections, into an observable. Or you can simply create observables programmatically. That's the last example. But just to show that. And if you have them, you can do a lot of interesting stuff with them. So the first thing that we would like to do is we get products from a merchant system with a really custom merchant-dependent data format, but we want one unified data format that is returned to our client. So the first thing would be we would map each item from this merchant system to our own internal data format. That can be done by map. Yeah, on the top you see the observable that is returned from this merchant2 system, and down there you see the observable that you get when you map that with a certain function. In our example, that would mean something like that. We get the products from the merchant system and we map them with some mapping function that creates a search result. Because we have many merchant systems, we want to merge these streams in the next step. So we have two streams, one from merchant system 1, the second one from merchant system 2. We merge them and we have a stream of both merchant systems. That's in code that looks like this. Yeah, I think it's pretty self-explaining. You have these both streams and you connect them with the word to merge with. The next step is a little bit more complicated. What I showed so far was, I go back a little bit. In this example, we are just on the right side here, what I showed so far, getting stuff out of these merchant systems with observable. Now we want to have a look on how to combine something that we get out of the search index with requests to the product and the inventory system. And yeah, that's what I want to show next. The zip function is combining two observables or two streams, uses a function on a combination of one item from each of these streams and returns another item. That might look abstract. Concretely, that looks like this. We want to get the product details for a certain product ID, and we create two observables. One is an observable for products from the product system that we retrieve for this product ID. The other one is we want to know how many of these products are still in our inventory system. And we want to create also one of these search result objects from that. So we have 3 input parameters. The first 2 are these observables that we want to combine, and the third one is a function that we want to apply. In this case, it's a constructor for the search result. And what we get is an observable of search result. And yeah, the next step is actually getting this product ID into this function. And yeah, for that we have to go one step higher. So we would get this product ID out of our search index, and we would map that. We would create an observable based on this product ID, but we are not interested in to have a stream of observables. We actually want to have a stream of the items of these observables. And in code that looks like this. So we would ask the product index. In this case, that is our Elasticsearch. And we would get a stream of this product IDs. And with this, we would call this product details function that I showed before. And yeah, flat maps actually achieves that. We simply have a stream of search result. If we would use just map, we would have an observable of observables that we don't want. Yeah. The question is, have we already achieved what we wanted to achieve? Because our goal was to execute that in parallel, right? We wanted to have, we didn't want to wait for that in sequence. We wanted to execute it in parallel. In the default, RxJava is executing everything single-threaded. So to get concurrency, you have two possibilities. The one is you can use schedulers. So you can tell an observable that it has to subscribe to some scheduler. There are different types of schedulers. They are specialized in I/O or in computing or whatever. In our case, because it's I/O, we subscribe to a scheduler. But actually, that's what I don't use normally, because the much easier way is to simply use Hystrix. So that's a command that I already showed before. Because each of these Hystrix command has its own thread pool, this part of our observable chain is executed in its own thread pool, and that causes that all these streams are executed in parallel. And this is exactly the same command that I showed before, that we can execute synchronously, that we can use with futures, but we also can convert it into a stream with observe. And from that we can simply construct our observable and get exactly the result that we like. And we use Hystrix command for all these external dependencies that I showed before. So the question that is remaining is, how do we return the result of all of this chain? And there it's very important to block in the end. It's very confusing in the beginning when you start using Rx, and I was really confused because in the beginning I was working on a static set of data and was really surprised that I received a different result for each call, and that was simply because I didn't block. So the main applications thread was simply continuing and was returning that was what he already received at the point where he reached the return statement. So it was really randomly what it returned. And when you want to be sure that you collect all results that are actually in the stream, you have to block it. And that's what I show here. Yeah. And that's actually already everything. So what I want to stress is that I showed you one way to do things, but I think the nice thing about the elements that I showed you, that you don't have to do everything at once. It makes completely sense to use Hystrix when you want to stabilize your system. It's not necessary that you move further in the direction of microservice when you think it doesn't make sense. You already gain a lot of by simply introducing Hystrix. Rx is a nice way to increase the amount of asynchronous processes in your application. You can't call it really a reactive application. It's more something that helps you to have some asynchronous processes in a certain area where it makes sense in your application. And from there you can move further in a more asynchronous way, of course. And also microservices. I think it really makes sense to move there step by step. You don't have to get rid of your complete system. You can start with a certain area of your application and simply start with one autonomous system in the first place and gain experience. And from there you can decide what the next step would be. And the nice thing is that your monolith gets smaller and smaller. And from my point of view, that makes a lot of sense. And I think you can get back some fun in your work when you actually control your systems again. And that was it already from my side. Any questions? Yeah. Actually, I had a short look into the completable features of Java 8. And actually, really, it's just one possibility of this approach. Yeah, there are many others. I think it makes sense to use it when you're already using Hystrix, because it simply has a nice integration into it. Yeah, so it's more what I want to show is this way of using streams. And which tool you're actually using, I think they all have disadvantages and advantages. In this case, I didn't have a look into Guava. So. Yeah. Yeah.
According to the slide, you use two programming languages in your project. Yes, Java and Go.
Yeah.
And have you tried to use Reactive programming in Go? And if not, what part of the project is written in Go?
Actually, this is just an example, yeah. And normally, I'm giving this talk together with a colleague, and this slide was from him. And I think he does a little bit of Go. That is something where I actually have no experience with. So it's yeah, it's really just an example. And I think what is there important is that you should have systems that are so small that you can make decisions on each domain. Yeah, you can say in this domain it makes sense to use this language, and in this domain it makes sense to use that language. With each of them, there are advantages and disadvantages. Yeah. Yeah. Yeah.
Is it really makes sense to use JavaDay? Does it feel like data flow for me?
Again?
Does it really make sense to use JavaDay because it does seems like a data flow for me?
I think it makes sense to parallelize stuff, and what I showed is actually something that Netflix is also doing. Yeah? They have an HTTP interface in their application, and then they have something that they called asynchronous facade. And to collect all this data, they are using exactly these streams. Yeah, and I think that makes a lot of sense. Yeah. Because it's easy, it's a I think it has a quite nice programming model. Yeah, it's simply in the beginning it's not so easy because you really have to get used to it. But I think the code is much more readable than when you do all of this manually. And it's just I just wanted to show it as a way you can choose. I don't say that it's the only way to achieve this. Yeah. Something else? So I think we are all also out of time. So thank you very much for listening. Yeah.